Hi everyone, so this is Miss Polly and this is our last lecture for this semester entitled as the Alternating Current or AC Circuits. Now, this is actually the pair for chapter 11, which is direct current, and I already discuss with you the stories of AC and DC, and today we will see more on what is AC circuits. So this is our subtopic for these chapters. We have a quite simple number of chapters for this subtopic for these chapters. Actually, we have first and foremost we will understand what is an alternating current, and then we will see what will happen when we connected these three main basic instruments of circuit with AC. So we will see what happened to the I, the resistance, and also the voltage itself. Okay, after that we will see combinations of RLC in AC circuits. So again, what will happen to these three when all these three was combined into one. Last but not least, in these chapters, which I'm not included in here, is one of the applications for AC circuit. It's a transformer. So we will discuss a little bit on what is transformer, and please pay attention to it. You might see these questions on your essay exams. So I'm continue with the first subtopic, which is alternating currents. So alternating currents, also known as an AC, yes, we call it as an AC. So our AC is something that produced, or current that produced by a generator, which has no directions. This is the keywords. There is no directions in AC in the sense that direct current has. So direct current, as you know, if this is my power supplies, and if the electron is moved towards here, then the current will move towards here, and vice versa. This is direct current. But in NAC, there is no particular directions for the current, because the symbol is like this. So it can be on the right side or on the left side, and the magnitude varies sinusoidally with time, as given as this graph over here. So bear in mind that I maximum, or current maximum, is always lower than the EMF maximum. So this is a graph or sketching of graph for current and EMF versus time. The red line is represent for the current, and the black line is represent for your EMF. Now, your power supply or EMF is also equal to this equation, where EMF is equal to EMF maximum sine with the theta. And similar with the current, the equations or general equations for current is I maximum sine theta. So this is a general equation and also graph for EMF and I maximums. Now, why does this graph is important? You will see a change of graph, or a change of starting for I maximum and EMF maximum when the AC circuit was connected with resistor, inductor, or capacitor later. Okay, Now we continue with the next subtopic, which is effective AC current. So what is effective AC current, or also known as I effective? So the average current in a cycle is 0 half plus and half negative, because the other part is on the positive axis, and then on the other side is on negative axis. So this is this is the meanings of average current. So to find the average current here, or also known as root mean square, I will use these equations. So IRMS, root mean square, is short form for shortened into RMS, is also equal to the square root of I square divided by 2. And when you divide this thing into square root, you will get 0.707. Hence, the equation for IRMS also can be written as this one, where I is equal to 0.707. So this is IRMS. Now the relations of this IRMS with the I effective is this one. The RMS value is sometimes called as a effective current, because this is the value that actually being used when you switch on your switch in circuit. So let's say I have a current with value of 5 ampere, and by calculating everything in my circuit, I observe that only 4.5 ampere that been used in all the functions of the circuits. So this is what we call as IRMS. This is the root mean square current that been used in our circuit, and this is also known as the effective current that been used in our circuit. So I effective is also can be written as these relations, where I effective is equal to 0.707 times with the maximum current. So in this graph right now, my I maximum is where the point is the highest. Okay, so the highest number, or the highest peak in my sinusoidal graph right now is represent the maximum current. Right, so that was I effective and also I maximum. Now we did explore about the relations of I effective and I maximum. It is also similar with the V effective and V maximum, because as you recall on my first slide of alternating current, which is the definitions of alternating current, you see a graph of EMF maximum and also I maximums, and you can see that the graph is actually similar to each other. The difference is I maximum is supposed to be lower a little bit than the EMF maximum. Hence, the relations of V effective and also V maximum in one circuit is also similar with the I effective and also I maximum. So this is the definitions of effective ampere and also effective volt. Right, so as I said earlier, one of the first subtopic is when we not replacing but put inside an AC circuit a resistor. So originally my circuit will be like this one without the resistor, but then when I put the resistor into this circuit, then I will get another additionals of basic instruments in my circuit. So what happened to my resistor or my V effective? Now suppose when I sketch the graph of this kind of circuit, I will get a similar graph from the definitions of AC circuit right now. So the graph, the sketching of the graph is supposed to be just like this one, where I maximum and V maximum will be plotting on the same graph, and I maximum will the value of I maximum will a little bit lower than V maximum. But then when the circuit was closed, the voltage and current supposed to be moved inside the circuit in phase, right? So for, let's say, what is the meaning of in phase? So for, let's say, at this point where t is equal to 5 minutes, for example, when t at 5 minutes, I maximum is at the maximum point. So the value of current is at the maximum number, right? And similar with the EMF or my voltage, at the same point, which is at t equal to 5 minutes, the V is supposed to be on maximum point 2. And at this point, so for, let's say, this is t equal to 10 minutes, it is discovered that V maximum and I maximum is at 0 value. Okay, so this is the meaning of in phase value. Now this is only happen when I put or add a resistor inside my circuit. So how to calculate the V effective of this kind of circuit? Now it is similar with Ohm's law actually. So Ohm's law states that V is equal to IR. So the V here in this Ohm's equations was represented as the V effective, and I is the I effective, and R is the value of the resistance. So that is when I put the resistor in AC circuit. What if I take out the resistor right now and replace it with another measurement instrument, which is in this case is inductor. We symbolize S and L. So as you know, the functions of conductor is to make sure that the directions of your current is in one direction. So that was actually the functions of inductor. Now for this case, before we discuss what happened to the AC circuit when inductor was substituted into this type of circuit, first and foremost, you need to know that inductor is one type of instrument that need to recharge and discharging. There is a process of recharge and discharging in inductor. So when it is recharging process in inductor, please refer to this first picture over here, this first graph over here. You can see that inductor, for, let's say, it is require 100% time to full a 100% ampere of current, which is the I maximums. So for inductor, when it is or the value of the current inside the inductor was reached this value, which is 0.63 times with the I maximum, we call the time required to reach this number is time constant T, right? Okay, please follow this part, right? So please understand carefully this part, because this is very important. Once again, I will repeat it once again. The time required to fulfill 0.63 of full current for the inductor, we call it as a time constant and symbolize as this number. Okay, now so for, let's say, the maximum current for this inductor, this particular inductor, because it is the maximum current that content in inductors is actually varies. Okay, so let's say this particular inductor has 20 ampere as the maximum current. So the time required to reach 63% from this 20 ampere is what we call as a time constant, right? And also this is when recharging process is happen, and vice versa, when your discharging process is happen, your time or time required to reach 37% from the maximum current is what we call as a time constant. So for, let's say, once again, I take this number as an example. So 20% is the I maximum of this particular inductor, and when it is used, the inductor was used, so it is experience discharging process. Now that discharging, when the charge was decreased until 37% from the originals or the initial number of the current for that inductor, the time required to reach this percentage is what we call as a time constant, symbolized as this one. Okay, so both of these symbol is actually similar in definitions. The difference is in charging process. Over here we need to see the number of 63%, and when the discharging process is take over, we need to see the 37%. So what happened to the graph of V, the power supply, and also the current when we replace the inductor or add an inductor into the AC circuit? As you can see over here, the graph over here, the sketching of current and voltage is a little different from the general graph, and also when the resistor is in AC circuit. Now, as you can see over here, the red one is represent the current and the black one is represent the voltage. And as you can see over here, let's say this point is t equal to 5 minutes and this point is t equal to 0 minutes. As you can see over here, the current is a little lags behind the voltage when the circuit was closed, right? So as you can see over here, when t is equal to 0, the voltage is start to rising up until one point where t is equal to 5 minutes, the voltage is at the maximum value. Meanwhile, the current at t equal to 0 hasn't started yet. It starts at t equal to 5 with the 0 value of current. And as you can see over here, so let's say this is t equal to 10 minutes. This is only for example. At t equal to 10 minutes, the voltage is starting to decrease to another smallest number of it. Differently with the current just starting to rising up from t equal to 5 and reach its maximum point at t equal to 10. Now this type of graph, we call it the current. Okay, the current was actually lags behind the V by 90 degree of theta. Okay, as you can see over here, voltage is already has the number at t equal to 0 minutes, but then current just only start at t equal to 5 minutes. So the voltage peaks 90 degrees before the current peaks, and one build as the other falls and vice versa. So the reactance may be defined as the non-resistive opposition to the flow of AC current. Hence, the value of resistance over here will be not similar with the value of resistance in your Ohm's law anymore. Okay, now we continue with the inductive reactance. In resistance or resistor, the value of the function for this resistor is what we call as a resistance, and that resistance is actually a number which represented by the unit of ohm. Similar with this type of circuit, when I add an inductor inside an AC circuit, of course there is a resistor or resistance involved in this type of circuit, because it is eventually one type of instruments of circuits where current is flowing through. So of course the existence of resistance is over there. But then in this type of circuit, we will not call the resistance of this circuit is resistance. Instead, we will call it as inductive reactance. Okay? Once again, what is inductive reactance? Inductive reactance is the one that opposes the current or the directions of the current in this type of graphene. And inductive reactance is similar with resistance in resistor, but as we didn't want to confuse with the original resistance, then we call it as a inductive reactance. The symbol of inductive reactance is XL. I believe if you already done your lab experiment, one of the lab experiment was introduced to you about XL actually. So if you done that experiment, you will have no problem to define what is inductive reactance. Right. So inductive reactance is a function of both the inductance and the frequency of the AC current. Hence, the equations of inductive reactance for inductance in AC circuit can be written as these equations. So inductive reactance is equal to 2 times with the pi times with the frequency of this circuit. Frequency will be usually from the AC supply, and times with the L. L is the number of inductance itself. So inductance was usually measured in Henry H, and frequency is in Hertz. Now by substituting these equations into the Ohm's law, because Ohm's law said V equal to I times with the R, since I will not call the resistance in inductance of AC circuit with the name of resistance, then I will replace this R with inductive reactance. Hence the equations of V in this type of circuit will be written as this one, where VL, which is the voltage that passing through in your inductance, is equal to I, the current in your circuit, times with the inductive reactance. Right. When I substitute these particular equations of inductive reactance into these equations of Ohm's law, then I will get a new expressions of VL, which is this one, where VL is equal to I times with the 2 pi times with the frequency times with L. Now, in these circuits, there is also what we call as I effective. So it is similar, the I effective here is similar with the one that you introduced earlier, where I effective, the the relations of I effective to I maximum is equal to times with the 0.707 with I maximum, then you will get your I effective. So VL is equal to I effective times with the inductive reactance. So this is how we calculate inductive reactance and the relations of inductive reactance with the Ohm's law equations. Right. So we come to the next instrument, which is our capacitance. So as you know, capacitance, the functions of capacitance was to store energy. This is the main function of capacitance. And hence, it is obvious to us that capacitance is also experience charging and discharging process. So the definitions of time required over here in this graph is similar with the one that I described in the inductance just now. So the time constant in the charging process over here, so this is charging process for capacitance. So time constants over here in charging process was the time required to rise or change or increase to 63% from the original currents. And in this charging process, the time constant was defined as the required time to decrease the number of current into 37% from the original number of current. So this is actually similar with the one that you introduced in inductor. Okay, now we continue with the graphing and also equations when a pure capacitor was added in AC circuits. So as you can see over here, a little difference with the inductor. This time my I was starting early and my voltage starting a little bit late, which that this voltage is actually starting 90 degrees after the current. So at this point, as you can see over here, the current was actually start at 0 and increasing until one point, where at this point the voltage just start up. Okay, so in this graphing, we call this the voltage, the current was leading the voltage by 90 degrees. So the current was actually start early with the value of 90 degrees before the current. So it is similar with the one in inductor. The difference is in inductor the voltage is start early, but then the current is lags behind. Okay, now as you can see the similarity between this and pure inductor in AC circuit, hence you know that a frequency was give a big impact to the value of V and resistance. Hence, okay, before we continue with the calculations or mathematics in this, I need you to know that similar with the one in inductor, where we call the resistance as inductive reactance, now in this capacitance, it is also change the name of resistance also change into a new name where we call it as a capacitive reactance. So the symbol of capacitive reactance is this one, XC, right? So for those of you who already finished with this experiment, you will actually know what is this XC right now. So XC is a capacitive reactance. It is similar, synonym with resistance, and also synonym with inductive reactance. And all these three has a similar SI unit where it is ohm. The difference is this capacitive reactance is just for capacitance, the inductive reactance just for inductor, and this resistance over here just for resistor, right? So the calculations of XC is a little difference with the XL just now. So XL is 2 pi frequency times with the inductor. Differently with XC, XC is equal to 1 over 2 pi times with the frequency and times with the value of capacitance for the capacitor. And when we substitute the relations, or when we relate the value of capacitive reactance with the value of voltage in your circuit, it is written as this Ohm's law. Just replace the value of R here with the capacitive reactance, and when we substitute these particular equations of capacitive reactance into this equation, we will see a new expressions of V which will equal to this one. So VC equal to 1 over 2 pi frequency of the times with the capacitance. So similar with the inductor just now, I effective is also in this type of circuit. So VC is equal to I effective times with the inductive reactance. Now there is an example video for these three subtopics, so please watch it differently. Okay, to end the three subtopic just now, this is a summary on how to remember who or which value in each circuit was legs or lead in each circuit. So I just need to memorize it by using this quote. Okay, it is said here, Eli is the Iceman. So in inductor, the EMF is leading by 90 degrees to the current. But then in capacitor, current is leading by 90 degrees with EMF. So this is the keywords or the words on how to memorize who and who will lead or lags in each connections of AC circuits. So Eli is the Iceman. Right. So that was the three single subtopics when R, L, and C was added into an AC circuit. What if I combine all the three things together? Now before that, I need you to understand one part of it, of the three subtopic right now. All the three equations and all the three graphing can be combined into one graph and into one equations. So the graph will be look like this one. Now it look a little bit messy, but when you understand on how to read this, you will have no problem to analyze any graph that include that involved in resistor and frequency. Now as you can see over here, the x-axis is represent the frequency and the y-axis is represent the resistance. So when I said resistance, it will be include your inductive reactance and your capacitive reactance, which is your XC and XL. Okay, so any number of resistance or any number that symbolized with ohm is all in y-axis. So as you can see over here, when R or resistor was added into your AC circuit, it will produce just a linear line over here, because frequency does not give any effect to the resistance in AC circuit. Okay, but then when we added an L or inductor in AC circuit, as you can see, the yellow line over here is proportional to the F. So when the number of XL is higher, the number of F is higher due to this relation, because XL is equal to 2 pi frequency L. When the number of frequency is higher, then the XL is also increasing. Okay, and last but not least, as you can see over here, the green line is when the capacitor was added into AC circuit. Now, based on this equation, XC is equal to 1 over 2 pi frequency C. When the value of frequency is increasing, then the value of XC will be decreasing, and vice versa of it. So it is represented by this green line over here. As the value of XC is decreasing, the value of F is increasing. Okay, so this is when we combine all these three together, XC, XL, and also resistance. Right, so by these equations, I will actually get a value of frequency. Now we will see it later, what is this F. Now before that, as a continuous, I will continue with our next subtopic, which in this subtopic, this is very important or highlight subtopic of this chapter actually. Just now, we already understand what happened to the resistance, to the voltage, and to the current when we added the inductor, the resistor, and also the capacitor in AC circuit, which separately. But what happened if we combine all the instruments together and added into AC circuit? So as you can see over here in this circuit right now, this is an AC circuit. How to know that this is AC circuit? Just look at the power supply over here. Okay, so AC circuit, the symbol of power supply will be usually this symbol. So I added another three instrument, which is my inductor, resistor, and capacitor in this series of AC circuit. So this will be hectic actually. We have our own resistor over here, we have our XL over here, and we have our XC over here. As for the current, it will be very easy because this is a series connections. So by logic, when the current pass through in this capacitor, it with one amount, this particular amount will also experienced by the inductor, because this is a series connections. Also with the voltage, so voltage will be very different with each other due to the number of resistance. Okay, because V is equal to IR. So when the resistance over here, and over here was different to each other, hence the value of V also different with each other. So what happened to this type of graphing? When we can combine all together in one, the graph will be look like this one. So it is a messy graph actually. Now before I describe on how to read this graph, I need you to know one point from this graphing. The white line is represent the value of V for resistance. The green line is represent the value of V of capacitance, and the yellow line is value for V in inductor. Now, as you can see over here, the y-axis is V and the x-axis is theta. So the general equations of relations between all these three will be written as V is equal to V maximum times with the sine theta. Now, as for the resistor, the white line, as you can see over here in this circle picture, as you can see over here, the value of V supposed to be a linear line because it does not affect by the frequency. Hence, the graphing for V will be sinusoidal just like this one, and it starts from 0. But then when you see the yellow line over here, which is the value of V for inductor, you can see that refer back again to the Eli is the Iceman. In inductor, the value of EMF is leading 90 degrees to the current. So as you can see over here, the value of V at 0 degree is actually very high, which is at the minimum point, because it is leading of current. It is leading to the current with the 90 degrees, right? So, and as you can see, the value of V at 90 degrees is equal to 0. But then the value of V at resistance at 90 degree just reaching the maximum value. And as for the volume of voltage in capacitor, as you can see over here, it is start at the bottom, at the negative point, because due to these relations, the current is leading by 90 degrees to the EMF in capacitor. So as you can see over here, at 0 degrees, the V will be at the bottom, and at 90 degrees it is equal to 0. Okay, can you understand this graph right now, right? So one more point in this graph is, as you can see over here, the value of maximum value of voltage for resistance is actually very high compared to these two. Okay, this is due to the influence of frequency. In VC and VL, frequency is playing an important roles to affect the value of V and also C. But then in resistor, the value of frequency is actually no effect at all. So that's why the number of maximum value for voltage of resistance is very high compared to these two. So this is when we combine AC with the three main instruments. Okay, so we simplify the graph right now to this graph over here, and simplify it again over here. As you can see, the x-axis will be the VR is exists on x-axis. Meanwhile, on y-axis, because VL is bigger than VC, so VL will be minus with VC over here on the positive y-axis. So the resultance of V between these two was actually what we call as a total voltage. So rules of theorem Pythagoras in mathematics, the positions of total voltage is supposed to be between this x-axis and y-axis, where the position or the angle between this total voltage to the x-axis is equal to theta. So this is the sketching, or this summary of sketching of the graph. Right. So we did summarize all the things, or the VL and VC and VR into our graph right now. So how to find this total voltage? As I said previously, this VT is actually in the positions of your hypotenuse when it is in triangle shape. So how to find the hypotenuse over here? By using the theorem Pythagoras. It's supposed to be used, or it's supposed to be calculated by using this equation. So VT is equal to VR, where this is x-axis square, plus with the y square, and the value of y in this graph is on by VL minus VC. So substitute in this equation over here, square it again, and square root of it, you will get the value of total of the voltage. And how to find this value of angle? Then again, by using these very popular equations, you will get tangent theta is equal to the total of V in y-axis divided by the total of V in x-axis, where in y-axis we have these 2, and in x-axis we have this 1. Right? Now, when we substitute these equations, when we talk about the total of resistance for these particular equations or this particular graph, we have a similar pattern of equations for the total of resistance. The total of resistance is what we call as impedance, which we will talk more in next slide actually, but then I will talk a little bit on impedance in here. So Z is actually the total of the resistance in RLC AC circuit. So how to find resistance? It is also similar actually with this equation, where impedance is equal to R square plus with the XL minus with the XC square and square root of it. So when we substitute the V into the Ohm's law, so we can see that this I over here will be constant, and the R is represented by the impedance, where the value of impedance is equal to this one, the whole these things. So this is total voltage. Okay, now we continue on what is impedance. Now we will talk a little deeper on what is impedance. Impedance is the total resistance in RLC AC circuits. Once again, I will repeat the definitions of impedance. Impedance is the combinations or total of resistance in RLC AC circuit. So in RLC AC circuit, I have 3 types of resistance, right? R, XL, and XC. So how did I sketch these 3 into a graph? It is similar with the V just now. The graphing is supposed to be like this one. So R is in your x-axis, and XL minus XC is in your y-axis. And impedance is in between these 2, where the angle between the impedance to the x-axis is what we call as a phase angle. Okay, so to find impedance, the equations was actually this one, because this is the equations to find the hypotenuse in triangle. So impedance was symbolized as Z, capital letter of Z, is actually square roots of R square times with the x-axis, y-axis, sorry. So y-axis over here was consists of XL minus with the XC square. Square root everything and you will get an impedance. So substituting again in Ohm's law, you will get a value of total voltage which is equal to the product of current and the impedance. Okay, so that was impedance. So we move to the next subtopic, which is this is actually more on the combinations between XL and XC. So what is resonant frequency? Let's say when inductance causes the voltage to lead the current, and in capacitance it is cause it to lag the current, they tend to cancel each other out. So when this happen, the resonance where when XL and XC is in similar number, then resonant, or what we call as a maximum power, will occur. So when this happen, then we can equal together these two value, the XL and the XC. So by rearranging everything to get this frequency over here single out on the other side, it will become these expressions. So what is this frequency over here? It is what we call as a resonant frequency. Okay, so resonant frequency is when the maximum power is happen. This is happen due to the XL is equal to XC. So resonant frequency is equal to this expression where 1 over 2 pi times with the square root of L times with the capacitance. L is the number of inductance and C is the number of capacitance. So that was resonant frequency. Now, last subtopic of this before we continue with the transformer is a power in AC circuits. Of course, when we talk about circuit, we will automatically talk about power. There is no point of a circuit when we can talk about power of it. So power in AC circuit, when the RLC was combined and added into AC circuit, the power can be calculated by using this equation, where P is equal to the product of I times with the voltage cos with the theta. Theta is the positions of impedance between the total of resistance or impedance to the x-axis. Now, power in terms of resistance will be also written as this one, where P is equal to I squared times with the R. Now, please take note that this cos theta over here is known as the power factor. So how big is this cos theta will be effect on how big will be the power of this RLC AC circuit. Now, I hope you are not tired with this with this chapter so far, because this is actually a very interesting chapters. Now, I will continue to the next subtopic, which is transformer. So I believe you did saw this somewhere, maybe nearest to your house or nearest to the building that you go every day or anywhere. So this is what we call a transformer. So what is the use of transformer? It is used to step up and step down the current or the power or the voltage in your circuit. Okay, so let's say I need to supply a maximum number of voltage in an area, so I will use this particular instrument. Now, usually you will see a transformer with a casing just like this one or this one. But then when we take out all the casing, it's supposed to be look just like this one. As you can see over here, the transformer was actually built of two winding coil, which is this is the first one and this is the second one. So this is actually a transformer. So what is transformer? A transformer is a device that we use inductance and AC current to step voltage up or down. Okay, as I said earlier. So transformer was actually built as this one. So we have what we call here as a conductor panel or conductor square or plane. So on the first side, where we call this part as a primary part, on the primary part we have this coil winding around with the particular number of turns, and it is connected with the AC power supply. When it is connected with the AC power supply and the circuit was closed, suppose it will produce a magnetic field. Then this magnetic field will hence produce a current, where the current will move or flow through this conductive panel, and it's supposed to be passing through this secondary part over here. On the secondary part, we have another turns of coil with particular number of turns, and this coil will be connected to anything, and in this particular example we connect it with the resistance so that the flowing of current will be controlled. Sometimes in a simple example or simple experimental, we just connect this one with the ammeter to observe the existence of current on the secondary part. So as I said earlier, when the current was flowing through this part, we can see a magnetic field. Another magnetic field here will be produced. So when the magnetic field was produced, then magnetic flux will be induced. Then with the induce of magnetic flux here, it will produce a current, another current, and that current is the one that we observe over here on the resistance or ammeter or anything that we connected over this side. So this is how the transformer so far working, right? So the relations of the EMF that produced in the primary and EMF that produced in the secondary, and the number of turns in primary and number of turns in secondary can be written as this one. So EMF in primary can be calculated by this equation, where it is equal to negative number of turns for the winding in primary part times with this is magnetic flux. We did learn this on the chapter electrostatic. So this is magnetic magnetic flux, and similar with the secondary EMF, we have a similar equation where it is a product between the number of turns in secondary times with the number of flux in secondary. So this is induced EMF up. When we substitute it, or we need the relations of the primary and secondary, then the relations is usually will be written as these equations, where these equations is actually what we call as a transformer equations. So transformer equations is written as this one, where the ratio between voltage in primary and voltage in secondary is also equal to the ratio of number of turns in primary with the number of turns in secondary. This is the derivations of this was actually between this one. I just divided these two things I will observe that these two can be cancel each other, hence I will get these relations. So this is what we call as a transformer equations. Right. Similar with circuit, there is no point to talk about circuit when we didn't talk about power. So similarly with transformer, there is no point we build the transformer when we didn't talk about the efficiency of the transformer. So what is the efficiency of transformer? It is stated that an ideal transformer can be written as this one. Okay, so when there is no power gain in stepping up the voltage, since voltage is increased by reducing current, the ideal transformer will be no internal losses. So this means that the efficiency of the transformer is almost 90% or 100%. So one ideal transformer is said can be reached this point. So when the voltage in primary or V in when the product of V and I in primary is similar with the product of E and I in secondary, or when the ratio of current in primary and secondary is equal to the ratio of voltage in secondary and primary, then this is the condition where we call it as a ideal transformer. So in ideal transformer, the efficiency are usually between 90 and 100%. So this is what we call as the ideal transformer. And that's all for this chapter. Yes, it is very short chapters and it is very direct to the point chapters, but then it is very complicated chapters too. So I will end this video here for the lectures, and you may want to see more examples in my video of examples to understand more on this chapter. So that's it. Thank you.